Okay, as we mentioned, we're going to talk about like camera today, camera model, and also calibration. So it's kind of weird because this is the last week, and now we talk about camera. And but anyways, just have some historical fun. I wonder like I know if you know the origin of camera. Actually, the word camera in Italian actually means worm. So as you can imagine, the camera used to be big, and it dated back like in the time of Greece and also like ancient Greece and also China. They have this kind of like dark room that is a huge, and then it's basically a pinhole camera that projected like I guess as a kid maybe you try that also, like you make a tiny pinhole and have some kind of image like far away, like the far away scene is able to project to at the back of like something like that, like an image like this. And this is like the camera, like Asian camera, and then like in during the period of Renaissance, like we have something like, let me remove this to the side. Um, we oops we have this this kind of like a treating device for artists. Basically, you can those people like suddenly you find that during the Renaissance times, like those painters just improve their technique so much. It's technology improved. Like they have this treating device allow them to just kind of see what they see like reflected on the kind of place that they try to draw. So therefore they can draw much better. Uh, and and then like actually if we think of like the modern camera as what we have now, photography doesn't the first photograph is actually is back in like 1826, and actually still you can find the photograph there is like stored in UT Austin, and it took like 8 hours to create that photo. And and now let's get back to something we are more like interested. So the materials I think of like now we have this modern cameras. I basically we have object in three-dimensional space, and now projected into 2Ds, and how we actually model those points there, like from objects from 3D to 2D. This is also just for fun, and there's another like kind of interesting painting, like also just for fun. I don't know. This slide is a little bit digression, but I wonder like if any of you can figure out like what is this thing like down here. Um, 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 it turns out that like such a skull, like it's from if you go down in a very kind of like, I mean, if you try to see it, I believe it's like from this corner, you're able to see a skull here. So anyway, really get to something technical. So just a very simple model. Like we have a pinhole camera here, and we have the image plane here. You have the object here. It's like the simplest like camera model here. So when we project this image here, like we have this image plane here, we can think of we have a virtual plane here, virtual image here. So we can still use this model like for modern camera. You can think of like when you see something like through a camera, it's like you have a virtual plane in front of your kind of camera. So maybe I let me try to, I don't know, maybe I use this one to draw. It's kind of okay. Um, it's easier to draw here, I guess. So what I mean is like something like so you have some objects here, like I don't know, some objects here, and you're seeing like a camera looking from here, right? And then basically you have a virtual plane, something like you see what you see, like, and you have a pawn, I project to here, here, so a pawn projected to something here. So then if you think of like simple trigonometry, so this like virtual plane, you let's say it's like maybe the distance from the lens, or from the sensor is like d from the virtual plane here. So let's say then and the actual object is like at the location here, let's say like x, y, and z here. So something like that. So what we see here, this point here, what we're interested in is like what's the actual location in this image, right? Like this is like the 2D image here. So you have the location here somehow x pi, y pi, let's say. And then now how do we project this one to this one here? So it should be pretty simple, right? Okay, maybe I didn't draw it pretty well. The point doesn't look like it should be somewhere here. So maybe the point is more like here. I guess I make more sense. If I draw like this is x pi, y pi again. And again, like this is like distance here is d, and this is this distance is c here, let's say, right? So so you see like this is like a similar triangle, right? This triangle and this triangle is like similar. Maybe I use different color or something. So what I mean is like, so this triangle here and this triangle here is similar. So therefore, like we have now x, y. So we should have like x pi over z. Sorry, over d should be over d should be equal to x over z, right? It's very simple formula basically, and you have y pi over d is equal y over z, something like that. Now, but what we want is that we want to kind of have a matrix form for that. You see, like I have this z here. Somehow this is like in the denominator, right? So if I project here, this is like it's not something linear. So remember that like we've seen something like that before. Like this is the limitation of using Euclidean coordinates. So we mentioned that like we can use this homogeneous coordinates that, so we have like instead of x, y, z, so we pad 1 here. So to make a so-called homogeneous coordinate, actually we talked about 2Ds in the past. So we have x, y, and say we remember that when we talk about like projection in homography and so on, like instead of like x, y in 2D coordinates, Euclidean coordinates, we just pad 1 here. We have x, y, 1 here. So this is the homogeneous coordinate. And so what it means in this homogeneous coordinate is that like if I have x, y, w instead, so the actual or like maybe I write like this, the scaling of this homogeneous coordinate doesn't change the actual location of the points. I mean it referring to, so if I ask as y and s, these 2 points are equivalent. So or like again, if I have x, y, w, this is actually referring to the point that like x over w, y over w in the actual Euclidean coordinate. So you guys are fine with all this, right? So we have seen all this before. Now we just extend this to 3D, right? So we have 3D homogeneous coordinate. So instead of xy pad 1 to xy1, we have xyz pad to xyz1 here. Now if we have homogeneous coordinate, you see I can have a projection at x pi, y pi. Let's see. If I have let's see, x pi d Okay, okay. I should have something like this. So if I have, let's say, how do I get what I want here? So what I want here is like, I want like x pi, the actual location. So x pi, it should be x over z times d here, and y pi is y over z times d here. So I can I can have that if I have something like a projection. Um, my cat's not happy. I didn't feed them today yet. So let's see. X. Yes, I should multiply by d here. So I multiply by d here. Let's see. And I multiply by d here. And if I have 1 here, I think it will work like this. So let's verify that this probably will work. So let's say if I have, this is the projection matrix for this one, projecting, let's see, I need to fit some zero here, of course, because otherwise, okay, this is a matrix of 3 by 4 here, so maybe I put all this zero back here. So what you see is that, okay, if I do a projection like this from this homogeneous coordinate to the 2D homogeneous coordinate, let's see what I have here. I have like this, it will be like dx, right? D times x, and all this is 0. The first one is just dx, and the second one will be just dy, right? And the third one will be just z. Now, and then like, and then like, okay, of course, this is correspond to, as I said, the scaling doesn't matter. This is actually is equal to dx over z, dy over z, and 1. And so therefore, like this is actually referring to this here, like this actual Euclidean coordinates dx over z and dy over z. So you see that like I can project a point in the 3D to 2D now using this projection matrix. When my focal plane or this projection plane is a d distance away from my camera center. And by the way, of course, I can do dd1, or actually more common, people will want 1 over d, because scaling doesn't matter, right? So I can have 1 over d will be the same projection as I dd1 here. So any questions for you guys? Like, this is very simple, but it is like also I think it's very important like to understand this kind of stuff. Like extremely simple, but yeah. And once you understand, you will always remember that like it's nothing fancy. So so this is what these several slides I'm trying to exactly present here. Like it's just repeating what we have here. I just mentioned. So I will have this use this homogeneous coordinates as I mentioned. So this is the 3D homogeneous coordinate. If I have this projection matrix by this one, I have the 2D homogeneous coordinate for this after the projection, and then that corresponds to the actual Euclidean coordinate like this. And this is known as the perspective projection. And that's used by the artists, right? When they do the drawing. And as I mentioned, like we can, instead of like dd1, it's more common. People use this projection matrix 1 over d instead. And that's what we actually have like for perspective projection. So you see like this in the game, like when you draw something, this is like really nice 3D, like you can see that like it's very much like have this 3D feeling. It's like using this perspective projection. So and there's also like something, a special case known as a holographic projection. This is a simplified version you see in 2D games, like this one. Like we basically what we did is like this is the Oh, okay. Actually, this is the homographic projection is like this. So it's like uh, instead of like basically what you see is like for the z component here we didn't do anything here. We just put a we okay. Uh, let me let me get my pen here. Let's see. Oops. How do I? Earlier you remember like for this perspective projection we have this is 0 here, this is 1 over d here. So but here like instead I have a 1 here, so therefore c is just get 1 here for this orthographic projection, and then x and y will be just project directly. So I have uv here is just equal to xy here. So and I can scale that a little bit, but in the sense it's just basically directly projecting this, like basically ignore the z coordinate here, just project like this. So and you can think of like this is like a light source from infinite. So you have like infinite that the shadow like a 2D project a 2D projection, a 3D object, if an infinite a light source like infinitely far away. So and this is homographic projection, and there's some variation that like we can change this scale a little bit. That actually this is like the with sometimes people known as this weak perspective. So that's like in what you actually what we have this like fake 3D like in like older games like in in the 80s or early 90s I guess. And we can also have this affine projection. That's basically what actually what we saw like in the when we talk about projection not projection actually um, how do we call that like at that time it's like this mapping like in 2D as well. So we also look at those like have affine projection, yeah, actually it's projection, affine projection, and also like at that time like if we also have like non-zero here, that basically all of this like basically you have this for the most general cases we just have this linear transform here, right? So if we allow to have like if you remember like if we allow all this to be arbitrary, then we have this homography here. But if we only allow the first two rows to be arbitrary, then we have this affine projection. So for this perspective projection, it's like homography, like we mentioned, and what is preserved. Like here, like this is like just basically this perspective projection is actually just an extension of homography from like 2D to 3D, right? I'm actually more precise, it's like 2D to 3D, then mapping to 2D. And in this case, we still have those similar properties that we mentioned in the past when we discussed homography, that the straight line preserved, like when you have a straight line, it used to be straight line, still will be straight line. And also like we will have like this so-called vanishing point appear in the scene. So like if you have parallel lines, so they will still be like straight lines, but they will like kind of converge to this vanishing point. So each pair of parallel lines will will kind of converge to a vanishing point, and if you connect all these vanishing points, you have a vanishing line. That in a lateral scene is basically just a horizon. So most often, like when you see a kind of a scenery photo, this vanishing line is actually just a horizon. Um, and there's more example like this for this vanishing lines and vanishing point here. So we have this um, um, I mean the vanishing point for some parallel line the vanishing point can also converge to infinity. So like this one here. So there's also vanishing point basically, but it's actually converging to infinity that you cannot see it here. Um, And what do I want to say for? Okay, there's more about this perspective transform. So lines, as we mentioned, I actually already mentioned that. Uh, so point-to-point lines to lines. So there's also possibility that there will be kind of like many 3D points will project to just a single point. It's possible when you're lying on this way here, right? For example, if I the candle, the tip of this fire here, if I along this line, okay, I'm not sure you can see I think you can see my arrow, right? Cursor here, right? So um, if I consider points along this red line here, all these points will project to the same point, right? Here, same points here. Um, uh, yeah. So and also plane, if you have like you can, it's possible for 3D plane will project it to either plane or to a line. That's kind of obvious. When they project to a line, will be something like you have 3D planes. For example, if I have plane that's parallel to this way here, then it will just become a line somehow. But okay, I guess that can't figure that out. This is very simple. Like just imagine like what will happen. I mean like you all of you guys are expert in this 3D environment anyway. You have been live in this world for like more than 20 years now. I don't think like there's anything amazing to you like for what we talk about here. So now what we are more interested here now is like we have this very simple model of projecting points like from 3D space into 2D space. And of course like we didn't mention any artifacts. We mentioned some artifacts like in terms of like we have this pinhole canvas models. Like how about we have this artifacts due to the curvature like of the lens and like the basically the imperfect model of the pinhole canvas because of the effect of the lens. And besides that, like because like we are in the original discussion here, we assume the center of the coordinate. Basically, we have the center of the camera is the center of the origin of our coordinate for the world model. It's possible that these two coordinates are not aligned with each other, right? So then we need to take care of that also. Then basically, as I mentioned, like this will be like we can have like two coordinate system. One is like the world coordinate, maybe the origin is here, but maybe we have like the camera that have a different coordinate that maybe the center of that projection is like different. So then like we need to align these two coordinates to one another. So what we can do is like let's say the world coordinate um oh, by the way, before that, like, okay, this slide is actually, I want to talk about the two different type of parameters. Here we have this extrinsic parameters is depending on the coordinate. Basically, that's what I just mentioned that like we have these two coordinates, uh, the parameters to align this one coordinate to another coordinate is this known as this extrinsic parameters. And then the intrinsic parameters will be like more related to the camera artifact. Uh, so for example, like whether there's some uh, perfectness. Yeah, is that the word supposed to be like that? I don't know. So um, something that is not perfect, like for maybe for the lens, like maybe the aspect ratio is not supposed to be one to one, or like we may need some adjustment for that. Like so, but okay, let's talk about the extrinsic one first. I try to align the coordinate. This is actually both of them I would say is not so complicated. Like, but uh, this is shouldn't be Okay, anyway, like it shouldn't be difficult anyway. So I have, let's say this is the world coordinate here. I have the camera coordinate here. So you see the origin can be different, but also like the axis, like the direction of the axis can be different as well. So in general, like you may have the camera coordinate with the vertical z. Of course, it can be different, right? When you tilt the camera, apparently it will be like not your camera, like you tilt like this. Let's say I have the camera here. So what I mean is like now the camera, the vertical axis is here, but if I point the cameras a bit upward, then my vertical axis now become here. This is the v-axis here, so they will be a bit different. Now, okay, I regret that I joined this. Let me just erase this. Yeah. Okay. So how do I align that? Like first thing, what I can do is like basically what I need to do is just translate this camera center to the world center, right? Whatever the origin that you're using for your world coordinate. That it will be just a simple translation, right? Afterward, you can do a rotation, basically rotation such that the axis will align. So the vertical axis V will align with this Y here, and this W align with this Z here, U align with this X here. So like this, first we translate, then we align. So how do we translate? Translate is simple, right? So let's say this is the world coordinates is like this. Let's say I have this origin of the camera, the camera center have the location C according to the world coordinate. So to translate this C to this origin, so we just need to have a minus C, right? So therefore I have a translation matrix is simply like this. Does it make sense? So I have the uh, original coordinate that let's see. Maybe I use this to write again. So I have the original coordinate that let's say x, y, z, 1. Now I transform to what? X minus c, y minus c, z minus c, and 1. So what should I do? This corresponds to multiplying a matrix 1, 1, 1, minus c, minus c, minus c, 1, right? And okay, I'm so sorry about that. So this doesn't make any sense at all. So this I have like two what I want to say is like xc the center, yc zc. Let's say that location of the origin c is like xc yc zc here, right? So it's like xc yc z zc like this. Right, so therefore the translation matrix is just like that, right? So and then afterwards, so you have this rotation here. Rotation turns out the rotation matrix is pretty simple. Also, it's like just UVW here. So let's see like why is UVW here. So let's see. So I have actually I'm thinking that maybe it's easier. Yeah, even though like I don't prefer to use PowerPoint, but I guess here it's actually pretty easy to just sketch from here. So I have the coordinate u is here, right? So what I want is like if I have along this axis u here, my let's see, Yes, I want to be like along this axis. It should be because I want to be along this axis, right? So if I along this axis, this should be my somehow this x coordinate. So therefore, let me. So therefore, along this axis here, my coordinate should be like 100, my new x, right? So for the x coordinate, the x axis, I should have 100, right? This direction should be 100, and along my y direction should be like 010, something like that, right? So now if I want this along this axis should be 100, let's see, then um, if I look at this axis here, let's look at this direction here. For this rotation, if I multiply by u, let's say multiply by this direction u1 here, okay. By the way, this u here is actually it's a vector itself. Like probably should be like ux, uy, and uc, something like that, right? So I have and so therefore this matrix here is more like ux, uy, uz, and vx, vy, vz, and wx, wy, wz, and 1 here. Now consider I have a point here. Let's say I have a point here that is a unit vector away from that basically I have unit vector, meaning that my norm u here is equal to 1. So I have ux squared plus uy squared plus uz squared is equal to 1. Oh yeah, that's expected because that's the axis, right? So I have, if I multiply by this point there, ux, uy, you see here 1. That exactly because I have ux, uy, uz multiplied together is equal to 1, right? So therefore, this one I should get 1, right? First one is 1. But now this v, this is basically actually the inner product of v and u, right? And v and u, because you see v and u supposed to be kind of orthogonal to each other, so it should be 0. So the inner product should be 0. And so as like w, like inner product of w and u, so it should be 0 as well. I hate this PowerPoint. Let's see. Okay. And then for the last one, it will be just 1. So you see that it map basically that basically the 100, the 100 coordinate in the original camera coordinate into 100 in the world coordinate, basically with this rotation here. So that's basically it. So you first have a translation, then you have a rotation, then you align the basically the camera coordinate into the world coordinate, and then so therefore I basically have a projection matrix like that. I first need to align my camera coordinate to the world coordinate, so that's basically do the translation matrix and projection matrix here. Then we have the projection. That projection is like what we have earlier, the perspective projection. So remember we have 1 over d here. So here we just make 1 here just for assuming d is equal to 1. So then this is basically the extrinsic parameters matrix. And then we have this intrinsic parameter okay, we're going to talk about next. So the intrinsic one, so basically the extrinsic one, as we see, if we multiply this one, this basically is like 1 times RT plus I times IT here. So this multiplied by this is what? Okay, let's see. This is equal to this, okay, we can do bulk multiplication, right? So we have 4 bulk here, basically. This upper bulk will be like R times I plus 0 times 0, so it's just R, right? And then this bulk here is now times T plus 0 times 1, so therefore it's just RT here. this lower block here is 0 times I and 1 times 0, so therefore it's 0 here. And this lower one is like 0 times t and 1 times 1. Wait a second. Yeah, 0 times t, 1 times 1. Those are therefore 1 here. So multiplying these two will be just equal to this guy here, right? Now if I do a projection for this guy here, so this, again, you can use this block multiplication. It's kind of easy. So think of this as like a block like this with a block like this. Of course, you can only do that like when you, what I want to say is like you need to make sure the dimension is right? So I have this R itself, like this part is 3 by 3 here. So this is like 1 by 3 here. This is a 3 by 1 here. This is 1 by 1 here. This thing here. So I can do this block multiplication if I make sure each of these sub-block, like each of these block, they can actually multiply. So in the sense like the dimensions should fit. So now if I have this block multiplied by, okay, again, like this is done, like this is equal to this guy here. This 2 multiplied is equal to this guy here. Now this multiplied by R here, and let's see, does it make sense? Yes, I think so. Yes, basically this multiplied by this will be just equal to, I only have 2 blocks now. Basically, if I multiply, I have 1 block at this multiplied by this block, and this multiplied by this is just equal to R, right? And then the next block is like this multiplied by RT, and this multiplied by 1 here. So therefore, I only have RT. So therefore, the whole thing, these 3 blocks multiplied together is equal to R times R and RT. So it's like this one. So you can sometimes you use small t to refer to this big RT here. So be careful, like this is 3 by 3 here, and this is like 3 by 1 here. And then I have this K matrix, right? Okay, I have intrinsic matrix. K is this one. I don't specify anything about this K yet, but for the extrinsic matrix now is replaced by this R and RT. Now for R and RT, if I assume that like originally like everything is aligned, then what will be R and RT? R will be what? Okay, I really should pause a little bit. Anyone can answer any question because it's so quiet now that I'm not sure that any of you are following. So if let me repeat the question and see if you can answer that. So if my original world coordinate, oh sorry, this is the camera coordinate, I think. This camera coordinate and the world, maybe I have used this part here. Go back to here. Let's say if I have this original camera coordinate and world coordinate aligned with each other, basically this CM0 is the same, and also like this axes are also aligned, basically y, mv, mu, mx, and w, and z, they are pointing the same directions. So then like in that case, I probably should clean everything here. In that case, what will be this extrinsic camera matrix here? Basically, what will be this R and RT here? Let me see, like any of you guys are actually here. I don't know how can I see participant is not showing participant. Oh yes. So okay. Anyway, anyone is following like
I'm trying to, but the internet connection at my place is not really good, so I'm really sorry.
Yeah, it's okay. Like, but should I repeat? Like, do you get my question here? Like,
No, I didn't hear it.
do you see the R? Okay. Where did you lost earlier? Like, do you get this R and T here? Like, So what was this? So basically, again, like we have this rotation matrix. So okay, the goal is that we have these two coordinates here. One is this camera coordinates, one is this world coordinate. So we need to make sure these two coordinates align with each other. That's the job for this extrinsic kind of camera matrix here. And and we derive that this extrinsic camera matrix is basically equal to this R and RT here. Now my question is like, in the ideal case, I'm not sure it's ideal or not, that if the world coordinate and the camera coordinates will already align each other like at the beginning. So if these two are already aligned at the beginning.
What do you think should be the identity matrix, probably?
Almost. Wait. So this one, so what will be this again? Like R, yes, R should be like identity. Yes, you're right. And then RT.
I don't know about RT.
I hear something. Maybe it's Brandon. Like, can you help?
Should be the magnitude. RT should be like the magnitude matrix.
RT should be T is the translation. So RT, okay, RT is 3 by 1. So T is just
It's like a vector of ones, right? Like
close. Okay. If I'm already aligned, if I already aligned. So yeah.
No.
So if we are already aligned,
It should be minus 1, I think. Because the x, so it's going to be minus 1.
oh, it's zero.
Yes, 0, because they are already aligned.
Yeah.
Yes. So T will be 0. So R as like as
they're already aligned. So the translation is 0.
Yes. So therefore, like that would be pretty simple. So our T in this case will be just I am 0. So therefore, like we will assume this ideal case first. So we ignore this extrinsic camera matrix. We just look at this intrinsic camera matrix. As you mentioned, so this intrinsic is like is considering any potential imperfectness, like artifacts like in the camera. So first thing is not really an artifact, but like because it's scaling, right? In this original camera matrix, like the extrinsic one, we didn't take care of the scaling here because in the projection we have 1, 1, 1. Remember, like earlier when 3D project to 2D using perspective transform, if we have the virtual plane here as a distance d here, then this will be 1 over d here. Here we just assume it's equal to 1. In general, you can have this virtual projection plane at any places. Depends on how you zoom your photo, right? Your camera basically. So therefore, like we have this zoom effect here. Basically, have a scaling effect here is d here. So the next thing is like we may not have aspect ratio. Wait a sec. Okay, next thing is like we may not have the center of the camera is actually the center of the world coordinate also. So we have aligned the camera of this. Oh, that's a little bit complicated. Let's the center of the camera with the center of the world, but the problem is like the center of the sensor. Okay, this would be the center of the sensor may not be exactly at the along this optical axis here. This okay, this is okay. I know it's a little bit stupid, but if it's not, then we need to have this adjustment here, like you not and we not here, right? So, but I know it's silly, but if it's not, like I assume like people should always align that. So then you have this U not and V not here. So next thing is like the aspect ratio. Like if we have basically like if we have one axis, it's like kind of like scale like differently from the other axis, then we will have one axis maybe is D, the other axis net to the make a change to alpha D here. And finally, it may even have like some skew effect here. Maybe the sensor is tilted somehow, like maybe become like this. Then you may need to have like S here just to take care of that. So finally, we will have a intrinsic kind of camera matrix like this. So overall, we have this extrinsic camera matrix, as we mentioned, is like just R and RT, or I can write like this. This is R here, and this T here is this small t, each element of this small t here. And then we have this extrinsic, intrinsic is like given by this one, like this one here. So this will be our entire camera models, like ignoring the radial distortion. So let's see. I have a kind of toy demo. Like I created like. Let's see if I can. Yeah, maybe I can. Okay. So this toy demo like this. I kind of pull out some point clouds. I did it a month ago, so I already forgot like where I got the point cloud. But I downloaded some point clouds. Then as I mentioned, actually I only play with the intrinsic parameter. I didn't play with the the extrinsic parameter, basically the coordinate like this R and T and so on and so forth. But didn't change the intrinsic. So I assume kind of ideal the intrinsic parameters. What I mean is here I assume basically I keep there's a scaling, of course. I assume that I can zoom. So basically I can vary D, but S will be equal to 0, alpha equal to 0. Oh, actually U0 and V0 I allowed to change that also. So basically I have D and U0 V0 change that, and then I have R and T, I can change that. Something like this, I think. Wait, can I go back to here? So so if I want that, let's see, where is it? Yeah, I have a scene somewhere like that. I don't know how, I forgot how to control it now. So you can see this is a kind of like a house, I guess, maybe. And I have this is like I don't know what is this actually. Some trees, I guess. And so I can move that. Yeah, I can move that. Move it up and down, I guess. And there's I don't know if you're interested. Okay. There's some theta t is basically okay. The okay, t is of course the translation here. Center 2D is basically the UV, like where's this, where I center this the sensor location here. So but theta, I can't forget what is that. Scale is like theta, I guess should be the angle of I think like, let's see, how do I change it? Okay, theta is like the different axis, the angle of okay. Now I can't like remember what I did probably. So my theta is my angle of seeing the object here. So let's say if I have a camera here, my theta is I have three different thetas. Okay, I don't know why I have three different thetas. So I okay. My theta is actually the camera matrix, the R in the camera matrix. So I can represent this rotation with with theta with three angles, right? Because this is just rotation, is rotate along three different axes. So that's my theta here. So, but it's kind of hard to interpret like the actual theta. So, but that's basically what's happening. So, I don't know. There's not much to say. I guess if I just do like this, maybe I would just like put it online also. Like if you're interested, you can just play with that. So, and let's see. And now I mention one more thing. It's also like, as I mentioned, like we didn't talk about the distortion due to the lens yet. So if we consider the lens distortion, it can have this kind of like uh, either like this pin occlusion or like this barrel distortion like this. So we can kind of mitigate this using this correction here. So basically, you just have a polynomial. Your xy will be replaced. Here is the you assume, okay. You assume the center of the sensor is here, and r is like the distance of pixel from this center location here. So then you can do this kind of fitting, just trying to correct whatever like this barrel and also like distortion effect. So it's like this distortion is like kind of like what should I say? So okay, I mean the distortion will be the same along this. It's okay. It's radial symmetric. I want to say that like it's radially symmetric. So therefore, you see, we can fix this distortion only rely on this kind of like effect on this scale like along this radial axis here. So and yeah, that's actually not much I can say about that. Like, but it's kind of okay. Okay, I'll just show you in a demo. Basically, you can take care of that using like, for example, like open series calibration. That will take care of that. So okay, like for I probably won't spend. Let's see how much time do I have. Yeah, here like for a camera calibration that we have, as you can see, the actual calibration is like we want to know this camera matrix, right? So if we ignore the final kind of radial distortion, then basically the whole model can be, whole camera model can be characterized just by this camera matrix here. That this camera matrix is basically what we have earlier, the extrinsic matrix multiplied by this intrinsic matrix there. And of course, you can many times also you can assume also the camera is reasonably ideal. So for the intrinsic parameters, if I go back here, often I guess you can assume that s is equal to 0 if it's the scaling effect is not too big, and also alpha is equal to 1. So if you don't have this artifact that like the horizontal and vertical aspect, the aspect ratio is not equal to 1. So then in any case, like the whole, if we combine that, like it just can be modeled by one matrix here. So then it's all again, like it would be just a fitting problem, right? If I know a lot of, not a lot, but if we know a set of points in the world coordinates that map into this coordinate in the screen, then we can just, if we have sufficient number of points, we should be able to just like approximate this M matrix back. So and so that's what we have here. So this here, like we assume this is the pair of points, like this is the 3D coordinates and the 2D coordinates here. So we have that. Actually, this is exactly you did also like in the homework for homography, but it just changed the problem a little bit, right? So now we just rewrite this here. The u okay, the because this is like the homogeneous coordinate xy, uv here is homogeneous coordinate, so we need to write compute also like this s here. So s is equal to this guy here. So that therefore the actual coordinate u and v is just equal to this this division here. And I have and then like I can rearrange the terms here as we did like also in the homography. If we put just we kind of like rearrange the terms and just rearrange the whole problems into something like that, right? So for each pair of points, we basically have again like two equations here, and then like this will be all the unknown here for this matrix here, and then like as what we have earlier, this can be solved using SVD, so kind of like or like eigenvalue decomposition. So I won't go into this again because we talk about that when we talk about homography. So and we reduce eigenvalue decomposition, then basically can solve that way. So solving this is the same as solving SVD. We're just trying to or like of course you can use eigenvalue decomposition as well. Then in that case will be like trying to eigen decompose a let's see I think I can decompose A transpose A, something like that. So then of course after you do SVD, you just find the one with the minimum single for the single vector with the minimum single value, and that will be the corresponding M vectors. Then you just rearrange, you can get back the M matrix here. So once you get that, okay, this is just weird. So once you get that, then you can potentially decompose back, try to find these values of R and T here. So note that the intrinsic parameter here. So even we assume the more general case, the intrinsic camera matrix is still like is a triangular matrix. So therefore, you can actually use some kind of like matrix decomposition to just decompose your calibrated camera matrix into like this intrinsic and extrinsic camera matrix. So and this is just a summary slides actually. Yeah, that's what I want to say. So if I get my M here, I can factorize back into this K times R. This is a intrinsic camera matrix, and this is an extrinsic camera matrix. And then like we'll use this RQ factorization. So basically we'll factorize into this will be like a upper triangular matrix for this K here, and this is a kind of actually what we should do should be like this. So this M matrix, after you construct that back, this will be like a 3x4 matrix, right? But if we only look at this first block here, this 3x3 block here, this one should be equal to KR, right? And for KR, we know that R is like a rotation matrix, therefore should be orthogonal. And K here should be an upper triangular matrix. So therefore it's possible to decompose that. So then like after you decompose that, like you find this R matrix here, this rotation matrix here. From R, you remember this T here is actually equal to RT here. So then therefore you can find the translation as well. So then you get basically everything. After the calibration, you should be able to know like what's the rotation and how far is your camera center from the world coordinate and so on. And that's basically what I just mentioned here. So you look at this only this part here and this part is actually equal to this multiplied this guy. This is orthogonal. This guy is triangular. And then after you find out, then you can find back like the translation. So and this is like for linear calibration. I won't talk about nonlinear calibration. It's kind of like more complicated, but probably OpenCV use that. But yeah, yes. So if let me just also do a demo for this calibration here. So here, like actually you can find the code like yeah, okay, I can share the code as well, but this is actually just kind of like we are running some of these things like from OpenCV tutorial. So let's see. Let's see where oh, okay, wait, should be somewhere here. So here is trying to look for a calibration board here. So let me, oh, okay, oh, where's my, I need to look for, oh, here. So I have a transport like that. This is a calibration you can find like also online. That's like they basically is trying to look for this point here in the and because it can't load the dimension, right? So therefore it will know the 3D coordinate somehow, right? You can approximate the 3D coordinate, and then like from that you get the screen in the 2D coordinates and oh wait a sec, actually I don't want to do that, right? But it's okay. I don't know whether I should break this. Let's see because well, okay, yeah, I can break this. I think I should add more fun here. So what I'm trying to do should be, let me see. Let's see if I can to find yeah, I add a kind of lens, kind of fisheye lens here. Just want to make some distortion for. So see if I. Oh, but that's a. Oh. Not able to find the. I'm trying to. Oh, that's bad. It's more this side maybe. Oh, I don't know why it's not able to. It refused to kind of like find the points here. It's just using, I guess like it can. Sometimes it's like a little bit annoying. So, but anyway, like, okay, maybe I will just give this lens and like, because I was able to do that like earlier. Is it really that difficult to find all these points? Yeah, I just don't move and then I just quickly. Maybe I should lower the number of required pawns here. I think I set it to 45 or something. Maybe this is the suggested number of pawns, but it takes so long to get enough pawns here. Okay, I'm almost done, I think. Yes. So the computer camera matrix, actually this using this calibration will take a while, I guess. Let's see. My camera is pretty slow. Sorry, my computer is pretty slow for some reason. And so this is not very interesting because originally it's not a lot of distortion anyway, so that's why it's not a very good demo. So that's why I wanted to put on the lens here. So this is supposed to remove the distortion here, like to make it more kind of like, but this I don't know. I guess I would just leave the code also like online. Then if you guys are interested, you can play with that. So yes.
What do you do with the results of that calibration?
Yeah, that's the point here. Like I couldn't like, so it would be better if I have the lens on, and then I think it have to do with my computer right now. I maybe say let's see what I'm running now. I don't think it's quite slow for some reason. So I guess it's maybe Zoom. So so what is going on is like if I have a huge distortion, for example, I have this lens. I guess you guys can see me, right? So if I have like huge distortion, like for example fisheye lens or whatever, so because of that distortion, the coordinate you get won't be accurate, right? Oh, okay. Maybe first of all, like what we're trying to do in the entire class now, we are trying to from like some 2D coordinates to get your 3D coordinates, right? For example, if you think of like what's behind you are doing this 3D reconstructions here, you are seeing something on the cameras in 2D. Somehow like you need to kind of find the corresponding points in 3D, right? And for doing that, at least we need to know where the 3D points is projecting into the 2D screen, right? So that's we need to kind of like generate this kind of matrix and so on. I mean to compute this kind of matrices and so on. And but if you but for this kind of matrix, the whole model here is assuming that there's no this kind of radial distortion. So if you have this radial distortion that, for example, appear in your fish lens camera, then you need to first address that before you do any computations. But did I answer your question? Like, is that your?
Well, I was just wondering like where the output is, but I guess it's there in input 14, then you use it in 15. What you're showing, right?
The output, yeah. The output is here. So that's the matrix is kind of like if we cover. Let's see. Let me just pin out the matrix here, maybe. So this is basically the camera matrix that I think this is the intrinsic camera matrix. So you can see this intrinsic camera matrix doesn't have this is the scaling here, the diagonal is scaling here, and the off diagonal is the scale here. It basically doesn't have much scale here, and the aspect ratio is pretty tight, right? So you can say scaling is almost the same. So this is like only the how far your cameras, the sensor center from your actual kind of like optical center. So yeah, but yeah, that's basically the camera matrix. Yeah. And I think like it should also have the yeah, and then you have this rotation and translation that can build you back the extrinsic camera matrix. That's basically R and RT that one, and this is the intrinsic one, right? After this one, it just create the own all the extrinsic and intrinsic. Also like you have this distortion is a radial distortion basically, and I think like this one here shouldn't be that. I don't know how. This is a polynomial things. Yeah, it's hard to like interpret like this. So, but okay. Anyway, I guess we are a little bit running out of time. So, you guys have any other questions?
Okay, so
Yes.
you mentioned there's linear and nonlinear calibration, I think.
Yes.
So can you just remind me what nonlinear? What's the difference?
Actually, nonlinear, like okay, I barely touch nonlinear at all, and I didn't prepare anything for that because, so we talk about this linear. We'll be just using SVD to decompose that. That there will be a linear because here you don't see that like we have assumed any radial distortion here. So, but for if I have a fixed lens put in front of my camera and try to calibrate, this calibration won't work, right? Because my distortion actually is nonlinear. So
So so a nonlinear would be like if there's like a lens distortion.
yes, nonlinear will be like you include as lens distortion. I mean the
Oh,
Open
okay.
Series demo here is like actually I think they did this nonlinear calibration, and for that one, that actually will be kind of like an optimization problem. So, and yes, and will be more complicated. But I guess we don't need to worry about that because we can just use the Open Series calibration. Yeah.
Great, thank you.
Yes. So, any other questions?
Most digital cameras include this calibration in the processing, right?
It depends on like what is your purpose here because I the calibration we need here is if we are interested to look at like what is the 3D points in the space correspond to like 2D points in the screen, and if you just take a photo we don't care, right? So therefore like they don't need this calibration. Only when like you are trying to do, for example, like 3D series construction, then we definitely need this. So yeah. But what I mean is like if you are doing like computer vision, for example, like OpenCV will include this kind of calibration. You will be able to calibrate like what I did, like just holding a board and like moving around, get the corresponding point, and then they try to calibrate. Yeah. So any other questions? So if not, I guess we will just stop here. Oh, and by the way, I received some question about the homework, but again, like please first like post your questions in Piazza. Uh, otherwise you're putting the T is really an easy job here. So just and when you post the question, just make sure that you include like uh, what's the actual error. For example, you try something, it doesn't work, and then say like what's the error there, so then like people can interpret, right? So it's like um, putting questions in a forum, like online forum, and I think it's actually a good exercise, like because after several years, many other years, I mean the materials here won't be. I don't know how many of these are useful, but to be able to ask good question in online forum is actually more useful than probably the materials we discuss here. So you can consider this as an exercise also, like ask a valid question. Like I I think like many people are trying to help, but like you need to be specific. Like what's the question? Like what's the actual problem there? So okay, I will talk to you guys like Thursday if you guys don't have any other questions and comment, um, and we can discuss more like about any potential problem for homework like maybe Thursday. So I will see you guys like Thursday then.